Hello, I'm Chandrasekhar Murapaka. I'm a faculty from the Department of Material Science and Metallurgical Engineering at IIT Hyderabad. So in the upcoming semester, I'm floating a course on functional properties of materials. So this course basically discusses about the macroscopic properties of the materials and how to understand from the microscopic behavior like atomic arrangement and electronic structure. So this course basically discusses about three important functional properties. First one is electrical properties, second one is magnetic properties, and third one is dielectric and ferroelectric properties. The course starts with how atoms come together to form solids. So basically depending on the different types of bonding, we'll classify solids as metals, covalent crystals and ionic crystals. Then we move on to electrical properties of materials. We will discuss about basics of electrical conductions in metals, and we'll try to understand the experimental electrical conduction from the theoretical model. So we'll consider electrons as free electrons. So basically like molecules in ideal gas, and we impose Maxwell-Boltzmann statistics to derive the model, and we'll try to see that whether this model, the Drude's model, can explain the experimental behavior of the electrical conduction. And we'll see what are the success and limitations of this Drude's model. Okay. To overcome these drawbacks, now we will consider electrons as quantum particles, as electrons have half-integer spin. Okay, so they are fermions, so we'll impose Fermi-Dirac statistics instead of Maxwell-Boltzmann statistics, and then using quantum mechanical theory. So Sommerfeld has derived a model to explain the electrical conduction, and we will see that what are the success and then again drawbacks of the Sommerfeld theory. And we'll see that even after this quantum mechanical modeling and also with imposing Fermi-Dirac statistics, we are not able to classify materials, okay, based on their electrical conductivity properties like metals, semiconductor and insulators. Then we'll try to understand why this is so, because we are completely ignoring the presence of ion cores in these materials and their periodic arrangement. So we'll bring in the interaction of the free electrons, okay, the electrons which we consider as free electrons with the ion cores, and then we'll change our boundary conditions from macroscopic to microscopic, and then derive a theory called band theory of solids. So from the energy and momentum diagrams, we will classify materials as metals, semiconductors and insulators, and we'll also derive a parameter called effective mass, which can capture a lot of information about electron in semiconductor devices. So with this we conclude the electrical properties, and we'll move on to magnetic properties of materials. So in the magnetic properties of materials, we will start with what is the atomic origin of magnetism, and then we'll try to classify materials based on their magnetic ordering, that is diamagnetic materials, paramagnetic materials and ferromagnetic materials, and how they behave in the presence of external magnetic field and why they are behaving in that way. And then we move on to ferromagnetic materials. We will discuss about domain theory of ferromagnetism, and then we'll talk about different types of magnetic ordering, that is ferromagnetic materials, antiferromagnetic materials, ferrimagnetic materials, and we talk about soft, hard magnetic materials and their applications. And then finally we move on to dielectric and ferroelectric properties of materials. So we'll define what is a dielectric constant, what is polarizability, how temperature and frequency can affect these properties. And then we try to understand what is electric breakdown, and then we'll try to understand what are ferroelectric crystals and classify them as piezoelectric materials, pyroelectric materials and antiferroelectric materials. So with this we will conclude this course. So if you are interested to learn about these topics, you may enroll for this course. Thank you.